In this video, we're going to be going over some pendulum problems. So first, let's start off with our example here. A simple pendulum has a length of 0.8 meters and it takes 18 seconds to complete 10 oscillations. Some of the formulas that you have to know with pendulums is that there's a period formula, and that formula is 2 pi times the root of LG. And if you rearrange this to solve for G, you're going to have G is equal to, actually remove the, because you know this is going to be for a pendulum, because here we're only going to be working with pendulum, so the subscript is kind of unnecessary. So if you arrange for G, it's going to be 4 pi squared times L over G. And in order to get that, so basically you see here, you can divide by 2 pi on both sides, and then this is going to cancel out. So then after that, you're going to have that L, that's square root of L. So after that, you have to take you have to square both sides in order to get rid of that root. Now after this, you have t squared 2 pi is equal to, after this, multiply by G, and now you have L, or sorry, don't multiply by G, we're solving for G, so you're going to multiply both sides by the root of L, or 1 over L, I don't know what I said, okay, and then here you have 1 over G, but if you want just G on the top, you're going to have to take the reciprocal of both sides, and then that's how you get this formula for G. Okay, so now let's tackle this question. For each of these 3 questions, we're going to find T, your period T, and you want to also find your value of G in newtons, or in newtons per second, and T is going to be in seconds. So let's do this. For this first question, I want to say, actually I'll just say gravitational constant. It's going to be experiencing different levels of gravity, so G in Newton per second, not times Newton per second, but yeah. So to start with this, we're going to have to find the T, your period, so that's going to be your total time over number of oscillations. So we have 18 seconds per 10. After this, we'll solve for G using our formula over there. So you're gonna have your length is 0.80 in meters. And that is your answer that you would get from plugging into a calculator, 9.75 meters per second squared. And this is close to the gravitational constant, 9.8 meters per second squared. So that's how you know you did it right, it's close by. Because it's on Earth, but it's also, you have to consider these factors when you calculate G for a spring, and also a pendulum, but here I meant to say pendulum. Here we're talking about pendulums. So, okay, for this kind of question. A pendulum has a length of 1.20 meters. It completes 25 oscillations in 55 seconds. Okay, period. So T is 55.0 over 25. That's going to be 2.20 seconds. Now for G, same formula here. Here, I want to keep this nice and neat, so I'm going to use these same formulas for all 3. So that's 2.20 seconds. You're going to have here 4 pi squared, length 1.20. All right. A pendulum of length 0.65 meters swings for 40 oscillations in 64 seconds. So we want to find period in G. So T is 64.0 divided by 40. That's 1.60 seconds. And after this, we have our G. Our G is going to be 4 pi squared. What is our length here? Our length here is 0.65. And we divide this by our G. Our G is going to be, or sorry, we divide this by, this should not be G. This should say T squared. Okay, that should say T squared. So 4 pi squared, 0.65. And you're going to have to divide this by 1.60 that we found up there for our T squared. And then you're going to get 10.02 meters per second squared. Close to 9.8 or 10. So that's good. So what we see here is that for all of our examples, when we saw that T increases, we see that G decreases, and that's because G is inversely proportional to T. Inverse relationship. Also, as we see L increases, then T is going to increase as well. That's because they're directly related to each other. Now, we can see that in our equation here. For our next problem set, we're going to do questions where we are going to find the period of oscillation, which is T in seconds. And you're also going to find the frequency. Your frequency is going to be in hertz of oscillation. So first, let's start off with period. So you have your period is going to equal to 2 pi times the root of L over G. And then if you plug in here, okay. So for this question, we had that our simple pendulum has a length of 0.50 and we want the period and the frequency. So how do we get that? We know that here L is going to be 0.50 and we're just going to use gravitational constant 9.80, and this is going to be equal to 1.42 seconds. Now for the frequency, that's going to be 1 over T, and that's equal to our period that we just found, the reciprocal of that. So that's going to be 1 over 1.42, and that's equal to 0.704 hertz. Now for our next example, a pendulum is 1 meter long. Find the period and the frequency. So T is equal to 2 pi times the root of L over G. So here we have 2 pi. Our length was 1. So you're going to plug that in, 1.00 over 9.8. And then that's just 2.01 seconds. Now for your frequency, that's just 1 over 2.01, your reciprocal of your period. And that's going to be equal to 0.498 hertz. A pendulum has a length of 0.75 meters. Find the frequency and the period. So we have our period is 2 pi L over G. T is equal to 2 pi 0.75 over G, 9.8 meters per second. And our answer is going to be 1.74 seconds. Our frequency is 1 over T, and that's just 1 over 1.74, which is 0.575 hertz. So again, what we see in these pattern of questions is that when you have a longer pendulum, so you have a really long string, it's going to result in a large T. You're going to have a large T, and you're also going to have a small f. And if you have a shorter pendulum, you're going to have a smaller t, and you're going to have a larger f. larger f. And you can think about this as well, like when you have a circle and you're just thinking about like rotational and angular velocity, or that means the same thing, but when you think of rotational velocity and when you're thinking about that linear distance that you're traveling, so think about it like this. When you have a circle, it's going to take less time. In the same amount of time, you're going to be able to traverse that entire circle faster than you were to traverse this larger circle, because it has a smaller circumference compared to a larger circumference, and you'd be able to travel that rotational distance faster. So that's why in the same amount of time, there's going to be more frequent revolutions of that, like traces around that circumference of that circle in comparison to a larger circle, because it's just less linear distance to cover. So now let's continue on with some more examples. So a pendulum completes 12 oscillations in 24 seconds. Find the period and the length of the pendulum. So in all these questions, we're going to find the period, and we want to find the length of the pendulum, and that's going to be L in meters or centimeters, and period is going to be in seconds, your T. So for this question, you have T is going to be equal to the total time divided by the oscillations, and that's going to equal to, here we have 24 seconds is our total time, and you have your number of oscillations is going to be 12, so that's going to be 2.00 seconds. So now if you have to solve for length, so using our equation from earlier, what we have here is our T equals to 2 pi L over G. So for this, we can just take this equation because we have L in here, so we can define this to be in terms of just L so that we can find our length. So to do this, we are first going to divide both sides by 2 pi. So upon that, that's going to cancel, and then we're going to see here we can take the root of both sides. We're going to square both sides. So then this root is, and the square is going to cancel out. And then on this side, you have T squared over 2 pi is just equal to the root, or sorry, just 1 over G. Or L over G, And then after this, you're going to multiply both sides by G. So if you do that, then this is going to cancel out. Your G's are going to cancel out. And then after that, you just have your L. So L is going to be equal to GT squared divided by 4 pi squared. Because you squared this. So actually, I just forgot to write 4 pi squared there. Now, after this, we can just plug in for our values for L. So now we have our formula for L. What are our things? So G is 9.8. T, your period, is 2 that we just found. And we're going to divide that by 4 pi squared. And that is going to be equal to 0.993 meters. A pendulum swings with a period of 1.5 seconds. Find the period. It's already given. And also find the length of the pendulum. So length, again, we're just going to use that formula that we had here. L is equal to GT squared. L is equal to GT squared divided by 4 pi squared. So L is going to be equal to what we plug into here. That's going to be equal to 9.8 times 1.50 squared divided by 4 pi squared, and then that's going to equal to 0.559 meters. A pendulum completes 30 oscillations in 45 seconds. So what we want to find is the period and the length again. Here, our T is equal to our seconds, our time in seconds, divided by our oscillations. And here that is our 45 seconds divided by our 30 oscillations, and that's equal to 1.50 seconds. So now we have to find our length. Again, we can use our length formula that we found over here. L is equal to GT squared divided by 4 pi squared, and plugging in, our L is going to be equal to 9.80 times 1.50 squared divided by 4 pi squared, and that is going to be equal to 0.559 meters and 1.50 seconds. So those are how you do those problems with T squared. And some takeaways that we have from here is that we can see here that our length is going to depend on T squared, and that's in a relationship that is L is proportional to T squared because they are both in the numerator. So that means that if our period doubles, aka you have t to 2t, that means that your length is gonna, your length will quadruple. So that means your length is gonna go to 4t, because you can think of it like this. You can use your proportional reasoning. You have L is equal to t squared, and then instead of t squared, you're gonna, I'll do this in a different color. You have L is equal to t squared, and instead of t squared, you can just write 2t and then squared, and then you're gonna have L is equal to, what is 2 squared? That's 4. So that's 4t. So if you plugged in 2, your double your t into the equation that involves L, and you keep L the same. So basically, when you do proportional reasoning, you're going to keep the other thing the same, and then you're only going to modify whichever variables you want to modify, and you're not going to include any of the constants. You're only going to have your variables, and then you're going to double it, triple it, halve it, and then you're going to see what that ratio of that simplified form with the variables is. So and there's going to be a factor, and that factor here is 4. So that's how you know that it quadruples, because of that 4 factor in front of the t, indicating that the period is going to double, or the period is going to quadruple, and the L is going to stay the same. So that would be the corresponding L for that. That would be the corresponding period amount that is quadrupled for that corresponding L length. Okay, now let's do some more problems. Derive G from experimental data. A pendulum of an unknown length is timed for 75 oscillations, and the total measured time is 150.3 seconds. The measured length of the pendulum is 0.995. Derive the formula for G in terms of a T and L. So we have our pendulum. Let's just draw this out. 75 oscillations and time. It's your time, your oscillations there. And our length is going to be 0.995 meters. We want our formula for G. Okay, so for this pendulum, our restoring torque is what we need to calculate. So it will go from up here to down there, and we can draw out the FBD for this. On our pendulum, you're gonna have the force of gravity that's acting on the pendulum at different positions, and also, okay, your force of gravity, and there's no normal force, it's not touching a surface. But here, we're gonna pretend that this angle that it swings at is gonna be a small angle. Even though here it looks pretty big, but it's okay, because this is just a really zoomed in version, so we can draw a really good FBD. But the reason why you want to have a small angle when you have these pendulum problems is because if it's a really large angle, that means your pendulum is going to swing in a whole bunch of different directions, and it's really difficult to calculate the period that way. But if it's a small angle, the directions that the bob at the bottom of the pendulum will swing won't be as diversified, and you can keep it constant. And also here, the bob mass is going to be negligible to the string's mass is going to be negligible to the bob, because the mass of the bob is going to be much larger. So for here, let's draw this out. You're going to have your mg going down, your F weight, aka your FG, and you're going to have here, this is going to be an angle. So this is going to be at an angle of theta. You can draw this here. So you're going to have this movement there, and this little line here, that's going to be mg sine theta. Mg sine theta, and this will also be mg sine theta. This is just theta here, and then this is also theta. And in your triangle, or you can connect this, what we consider this to be, we have x is equal to L theta, and this is your length right here. So we have that the period of a simple pendulum can be written as t is equal to 2 pi root of L over G. And we have for small angles theta, you're going to have F is equal to 1 over 2 pi times the root of G over L. So here in our pendulum, our restoring force that we just drew out for our free body diagram is equal to the torque of negative mgl sine theta. And here, sine theta is going to be approximately just theta. So that means that you have torque is equal to negative mg L of theta. So you can use Newton's second law, and that's just torque is equal to I, moment of inertia, times acceleration, angular acceleration. And we know that for a point mass pendulum, you have I is equal to ml squared. That's like I is equal to mr squared. But here our radius is equal to L. So also, you don't have to know this for AP Physics 1, but angular acceleration is equal to d squared theta over dt squared. So if you plug this in with your angular acceleration into Newton's second law, you would have torque is equal to, and you can sum your total torque, which is your IML squared. So what you're going to have is your ml squared d squared theta over dt squared is equal to negative mg L of theta. So after this, you can cancel out your ml. You see that on both sides. And your L. And you can rewrite this to be L d squared theta over dt squared is equal to negative g theta. That's because you have one left over L over here, by the way. And you have d squared theta over dt squared plus g theta over L is equal to 0. So that's a match of the simple harmonic motion equation. SHM equation here. That's going to be d squared x over dt squared plus omega squared x is equal to 0. So that means that we can say that omega squared is equal to g over L. And you just take the root of both of these sides. Omega is just equal to the root of g over L. And we know that using our period, we can connect this. We know that we know that omega is equal to 2 pi over t. So that means you can just sub in omega here. And you're going to have 2 pi t over t is equal to the root of g over L. And if you just square both sides, you're going to have 4 pi squared over t squared is equal to g over L. Now, if you solve for g, you just multiply both sides by L. And g is equal to 4 pi squared L over t squared. So we just got this formula for g squared, or for just g. So now we can calculate g and our period and all of our things. So let's first start with our period. T is going to be our you multiply both sides by t here, you're going to have t omega is equal to 2 pi over nothing. And then you divide both sides by omega here. You would have t is equal to 2 pi over omega. So here our 2 pi over omega could be used. And what do we have? We aren't given our omega, but we are given our 150.3 and our 75 oscillations, so we can use that definition as well. So we're going to use our time in seconds over our oscillations. Now let's calculate g using our formula that we found. That's 9.78. Now, after this, we can use percent error in question 4. So percent error, the formula for this is going to be 9.78 minus 9.80 divided by 9.80 times 100, and that's equal to 0.20%. Compare the two planets. A pendulum on Earth has a 1.20 meter length and a period of 2.20 seconds. The same pendulum is taken to another planet where its period is 3.10 seconds. So, derive how period depends on g. Find the gravity of the new planet and what is the ratio of these two gravities. So, what is our period formula? For 1, t is equal to 2 pi times the root of L over g. And as we've seen earlier, if you rearrange that, that's g is equal to 4 pi squared L over t squared. Now, let's do a check of the gravity on Earth. So that's 4 pi squared, and that's 1.20, and we have 2.20 squared. I'll highlight these so you see where they come from. Period 2.20 t. And we have our 1.20 L there. So, and if you plug this in, this is going to be 9.79. So now we need to find our new planet gravity. The planet. And we're going to take the ratio of this after. So you have 4 pi squared. 4 pi squared times 1.20 divided by 3.10 squared. And then that's going to equal to 4.98. So now we have to find the ratio of this. So that's going to be gravity of the planet over the gravity of the Earth, and that's going to be 4.98 or 4.93 divided by, this is 4.93, divided by 9.80, and that's going to equal to 0.503. So therefore we can say that the gravity on the planet is half of Earth. Pendulum in an accelerating elevator. A pendulum of a length of 0.75 meters is inside of an elevator accelerating upward at 2.5 meters per second squared. Derive the effective gravity expression, find the new period, and compare to a normal period. Okay, so what is effective gravity? When you have effective gravity, that means that you have gravity, you have a gravitational constant, means you have a gravitational constant plus a consideration of another force that is accelerating that object. You have to consider acceleration as well when you're considering effective gravity, because this is the effect of gravity with something else. So here we have our upward acceleration. We have it's accelerating upward, right? So the pendulum is going to be like this. Or you have your point here, and your pendulum is like this, and it's going to be accelerating upward. So that means that it's going to up here. If it's going up, our pendulum is, or I'm going to do it with a small angle. It's going up right now. It's going to follow this path to be here. So what do we need? Our upward acceleration, you're going to have G effective is going to be equal to gravity, which is going to be in our y-axis here. You are going to have gravity, Fg, and you're going to have your acceleration, which is A. So here we're going to just define that gravity is going to be G, and your acceleration is going to be A. So if you calculate your effective gravity, that's 9.80, and we have our acceleration, which is 2.5, so that's equal to 12.3. Now we have to look at our period formula. In period, it's 2 pi times the root of L over G effective. So that's going to be 2 pi. And what is our L here? Our L is 0.75. And our effective gravity is 12.3. So this is equal to 1.55 if you plug that into your calculator. Now, what is your normal period? This is for your period of your planet with your, or wait, that's the last question. This is T for the accelerating upward. So that was our answer, 1.55 periods. And what would our T be if our pendulum was just at rest? Pendulum. So this would be our 2 pi times the root of 0.75 divided by 9.80. So this would be if you were considering, so this is when you are at 1.55. But let's say, I'm going to make this pink. And what if you were here though? This has acceleration. So if you're just here, this would just equal to 1.74 if it was at rest. So how can we compare these? We can take the ratio if we wanted to, T rest over T accelerating upward. But overall, what we can see is that when the elevator is accelerating up, your Fg is going to increase. So that means your period will decrease. That's because we can see that this in this formula right here as when our Fg is going to increase, your period is going to decrease. So let's say you have a really large Fg. That means that your L, you're going to divide like a number divided by your gravity. So you have like T is equal to 2 pi. And you have 1 over 100. So that's going to be the root of a really small number. You're going to have the square root of 1 over 100. That's going to be a super small number. And you're going to multiply that by 2 pi. 2 pi is going to stay the same. So overall, your T is going to decrease when that happens. So that's why we can say that these are inversely related. Inversely related. Period and gravity are inversely related. So I want to recap here. Period is independent of mass because it's not in the equation. Period is proportional to the root of L. Period is inversely proportional to the root of G. Might as well just say proportional to the root of L. And G effective changes your T because it's in the formula. In this video, we're going to do some pendulum practice problems. So for a 0.5 kilogram bob that is attached to a 1.2 meter light string and released from rest at an angle of 35 degrees from the vertical, we're going to assume no resistance. We're going to have to find the speed of the bob at the lowest point. So let's start off with question 1 of this larger question. So let's draw out our pendulum here. Our pendulum, we're going to have at a point like this, and it's going to be like this, and let me adjust this to be a little bit smaller. So the angle that it's gonna swing at is gonna be 35 degrees, and we're gonna assume no air resistance. So our mechanical energy is gonna be conserved. So what does that mean? That means that we can find the energy at these different points that it is at when it is swinging as a ball. So when it is at this point up here, at release, when you release it, it's going to be released from the top at an angle at 35 degrees. So this is going to be the initial state. Initially, what we have is kinetic energy is going to equal to 0, and PE is going to equal to mgh. You're going to have gravitational energy at the top. So we can write this equation as our UG, because we only have UG here. And then when you're at the bottom, we're not going to consider this other part because we're considering just these two positions right now. So EF is going to have potential energy, and it's also going to have kinetic energy, but kinetic energy is going to be able to be replaced by 1/2 mv squared, and our potential energy is going to be equal to 0 because it's at the bottom and it is not having any gravitational potential energy. It's because UG is equal to 0. And here I'll write that too, kinetic energy 0. And we can write this as mgh. So after this, you can write your conservation of energy equation. Your initial energy is going to equal to your final energy. And what you can do is you can write your initial energy, mgh, here, and then you can write your 1/2 mv squared here. So you're going to have your gh is equal to 1/2 v squared because you have m on both sides, therefore m is going to cancel out. And then you're going to have gh. So what you want is you need to multiply both sides by 2 quickly, and then you can cancel out that 2 here. No, not on this side, on this side. And then you have 2gh is equal to v squared. So now you have this. So you can just take the root of both sides, and then you're going to have that cancels out. And then v is equal to the root of gh, 2gh. So after this, we can find h, the height that is dropped. So by using h is equal to 1/2 or 1 minus cosine theta. We have this is our L. So we have L 1 minus cosine theta. You're going to have 1.20, 1 minus cosine 35 degrees. Cosine 35 degrees is equal to 1 minus 0.819, and that's 1.20. So this is going to equal to 0.217 meters. Now we have to find V. So now we have our height. We can actually plug our height into our V equation. So this is going to be this right here, and you're going to plug that in right there. So your velocity is going to equal to 2 times your gravitational constant 9.80 times 0.217. Now that's going to equal to 2.06 meters per second. So that's your answer for your first part. This is for part 1. Now, oh, where did our question go? You might be asking, what do we mean by release from horizontal? So when we say release from horizontal, this means that the string is going to be pulled parallel to the ground. So that means that the bob starts at the same height as the pivot. Bob is going to start at the same height as the pivot. So the bob is going to be raised to a vertical equal to the length of L. So what we know was U initial was equal to MGL, right? So that was the speed at the bottom. We can get, from this, we get the speed at the bottom using conservation of energy. So we know that at the minimum condition at the top, t is equal to 0, right? So that means that was why we had mg was equal to mv squared over L, and that was where we got v top equal to the root of GL. Now, because we had to think with energy, right? We have here our delta U. I could just rewrite this as plus 1/2 mgl 5/2 mgl. By subbing in this. Because we know that 1/2 of mv top is what we have here. So then you just substitute this in here with the 2GL. And then you, with your 2L here, that's where you get that delta U. So that's where we got this 5/2 stuff over here. This is another way to prove it. So that's why we have, again, no loop.